Freddy, my boy, what are you doing?
Just hanging around.
Why are you upside down?
I'm not upside down, you're upside down.
That's because your frame of reference is inverted from mine. Were you seeing from my perspective, you would see clear as day that it is you who is upside down at this moment.
That is fascinating. But is there a universal frame of reference, one where observations can be made objectively, a point from which we may truly understand the nature of things?
No. As you can see here, the wall behind this figure appears to be moving. However, this is simply from the figure's frame of reference. In actuality, the figure was the one moving, the wall remained fixed the whole time. Now, let's actually move the wall. You can clearly see it moving relative to everything around it. However, if we were to restrict our field of vision and see the figure's frame of reference, it becomes clear that from this perspective, there is no way to tell the difference between the figure moving and the wall moving, since in both cases we see it from the figure's frame of reference. Their movement relative to one another was indistinguishable from a single frame of reference. All motion between bodies is relative.
If you've ever been to an airport, taken the subway, or went shopping in a mall, you've probably been on an escalator. If on an escalator you stood still and closed your eyes, what would you feel? From your perspective, you may feel as you were not moving at all. But what would your friends see waiting at the top of the escalator? To them, you'd move at a constant velocity. Now what if you were impatient and decided to walk up the escalator? How is the speed at which you're moving your legs related to the speed of the escalator? These are all key ideas to consider when discussing motion and moving frame of reference. Take a look at this cart. For this demonstration, we'll assume that there's no unbalanced forces acting on the cart, resulting in an acceleration of 0 and a constant velocity. When the cart is given a push, it begins to move along the surface of the board. If an equal amount of force is applied to the cart from the other side, the cart will roll in the opposite direction with the same speed. If we take a step back, we can see that the board that the cart was rolling on top of was actually moving across the surface of the floor with its own velocity. You probably did not notice this because you were watching from within the same moving frame of reference as the cart. Now let's look at the same demonstration from a fixed frame of reference. In the first trial, the cart moves along the surface of the board in the same direction that the board is traveling in. In the second trial, while the board moves towards the right, the cart is pushed towards the left. Watching the two trials side by side, what do you notice of the cart's velocity relative to its surroundings? The second cart appears to be traveling at a much slower speed. How are the velocity of the cart and the board related? Let's call the velocity of the cart u, and the velocity of the board v. When the two are pushed in the same direction, the effective velocity of the cart from a fixed frame of reference is equal to the sum of u and v. When the cart is pushed in the opposite direction that the board is moving in, its velocity is equal to the difference of u and v. This expression u plus or minus v does not apply in scenarios with extremely high velocities. In such cases where the velocity of an object approaches the velocity of light, Albert Einstein's special theory of relativity must be considered. However, in most situations that you're likely to come across in everyday life, such as walking back and forth in a moving vehicle, this expression is accurate in describing the motion of objects in a moving frame of reference.
So, in the vertical frame of reference, we look at the ball, and when it is dropped without moving, it goes straight down to the ground. Now, if we put it on a cart, as you'll see in the video, it will be moving at a constant velocity with the cart, and you'll see that to the cart, it will fall straight down. As you can see, the ball is moving at a constant velocity with the cart, and as it gets dropped, it falls in a straight line. So where the ball was dropped here, with the cart, it moved in a straight line.
So as Cam was saying earlier, with reference to the cart and the ball moving at a constant velocity, the ball moves straight down. However, if we use a different frame of reference, such as the wall behind the cart, which is attached to the earth, the ball, you will see, moves in a different path than the frame of reference with the cart. The ball will actually move in a curved path rather than a straight down path. This is because while the cart is moving and the ball is moving, the wall behind it is not. We will see this in a video. However, in this case, the wall behind will have two frames of reference, vertical and horizontal, so that you can see the relative path of the ball. Now, if we go back and trace the path of the ball, we can see that the ball actually, once it is dropped, travels in a curved velocity. Its horizontal distance traveled with reference to the Earth is that much, and its vertical is that much. However, its path is on a curve rather than straight down.
On a rotating table, the hoverpuck moves in a straight line. When the table is rotating, the velocity of the hoverpuck stays the same, only the frame of reference from which we're looking at is moving faster. Therefore, we're in a moving frame of reference. On the rotating table, when the hoverpuck moves across the table, the velocity is of the hoverpuck relative to the table, but not relative to the person observing in a fixed frame.
Constant velocity in a fixed frame of reference. A hoverpuck moves straight across the table with a constant velocity because the force acting on it are balanced. There is a little force on the friction acting on it. This is also commonly known as the law of inertia, which states an object at rest or in constant motion will remain at rest or constant motion unless an unbalanced force acts on it.
Rotating table, puck has circular motion. When the puck does not travel straight, but instead in circular motion, does it prove law of inertia wrong? It should go in a straight line if there is no unbalanced force present. Puck is almost frictionless. When we look through the Earth's fixed frame of reference, there is no unbalanced force acting on the puck. But in the rotating frame of reference, there is an unbalanced force as the velocity of the puck was not constant. This type of force is known as the fictitious force. This force is present in non-inertial frames of references. These frames of references exist when Newton's first and second laws are not valid. Accelerating frames of reference are always non-inertial. In this case, the rotating frame of reference is non-inertial. Every object that has uniform motion in a circle has an acceleration towards the center of the circle, which is known as centripetal acceleration.
Centripetal force and centrifugal force. Holding on the hoverpuck so that it moves in a circle is basically exerting a centripetal acceleration on the puck. When the object is moving with a uniform circular motion, the object is always accelerating, and the centripetal force that is being exerted on the puck is the same direction as the acceleration. If any time this centripetal force is not being exerted, the puck will move with uniform motion in a straight line that is tangent into the circular path which is moving.
This is the only horizontal force acting on the puck. The outward force, which is trying to make the object move away from the center, is a fictitious force, which is known as the centrifugal force. When we're in a fixed frame of reference, there is no centrifugal force. The force away from the center is an unbalanced force which is experienced by the person who is holding the object. To us, the centrifugal force is fictitious. It does not exist.
The question is this: do the stars and other celestial bodies orbit around the Earth, or are we simply rotated on our axis? Now, humanity has been pondering this question for hundreds of years, but the solution is very simple and can be demonstrated with this pendulum. Now, a pendulum is simply a weight affixed to a fixed point, which allows it to swing back and forth as so. Mounted on this rotating table, we can view the pendulum from two different frames of reference: the inertial frame and the non-inertial frame.
An inertial frame of reference is a frame of reference that is at rest or moving in constant velocity. In an inertial frame of reference, Newton's law do apply. Newton's first law states that an object's object will stay at rest or in constant velocity unless acted upon by a net external force. Newton's first law is also called the law of inertia. Inertia is an object's property to stay at rest or in constant velocity. Therefore, a pendulum swinging on a rotating table would be an inertial frame of reference if there is no unbalanced force acting on it. An inertial frame of reference would be the Earth's fixed frame of reference. When a pendulum is fixed to something like the ceiling or the lab bench, the pendulum would be moving in straight lines with a constant speed because it has inertia and there isn't any unbalanced force acting on it.
Now, a non-inertial frame of reference is an accelerating frame of reference. In this frame of reference, Newton's laws do not apply. This pendulum, swinging on a rotating table, would be considered a non-inertial frame of reference if there is an imbalanced force acting upon it. Now, a non-inertial frame of reference would be relative to the rotating lab stand that is attached to the rotating table. The rotating frame is an accelerating non-inertial frame of reference. It is so because the object moving in a circular path has centripetal acceleration towards the center of the circle. An object going around the circle would always be changing direction, and therefore always accelerating. In a non-inertial frame of reference, such as this rotating table, in this case, the pendulum would be moving in a deflected path because of the absence of inertia. Hence, Newton's law do not apply. As the turntable spins, the pendulum will appear to be spinning at the same rate as the turntable, but in the opposite direction.
These two scenarios demonstrate that the pendulum is not moving in reality. In fact, we are the ones that are actually moving with the Earth. In the first scenario, the pendulum continued to travel in constant velocity along a straight line because it was absorbed through Earth's fixed frame of reference. In the second scenario, the pendulum's path was affected by the motion of the rotating table, which represents Earth's rotation. In reality, the pendulum would be rotating at the same rate as the Earth's rotation once per day. If the Earth is not rotating around itself, the pendulum would be moving along a straight line forever because there isn't any unbalanced force acting on it. However, the pendulum was shown to be rotating in the non-inertial frame of reference, providing that there is an unbalanced force such as air resistance acting on it that was caused by Earth's rotation.
In conclusion, a pendulum can be used to prove that objects in space, such as the stars, do not in fact orbit around the Earth. In fact, the Earth is rotating around itself. In addition, Newton's laws do apply to an inertial frame of reference and do not apply to a non-inertial frame of reference.